Okay, so what I'm going to talk today is about activities in my group back in DTU Photonic on how to cope with one of the demands of one of the segments of the optical fiber optical networks infrastructure, which is the short range and the metro access. But before I start, I would like to introduce my group. So the name is Metro Access and Short Range Communications. And in order to do that, I would like to put this picture, which is, you have seen it many times and we are all acquainted with it, but it's to look that, if we look at this part, is where there are many of the talks covering today, looking how to bring the fiber to the home or inside the homes, or there has been a lot of talks on how to cope with the demands for data centers. And of course, all these segments connect somehow with the fiber, with the higher layers like the metro access and the core. So I'm going to concentrate somewhere around this part, and this is the activities, most of the activities of my group are focused on. And regardless on where do we look at, so there is a set of constraints or a set of challenges, and those can be grouped like this. So first is the capacity, so let it be in the metro, let it be in the long haul or in the data center. There is a need for increased capacity. We would like to connect as many users or many servers or many racks as possible with constraints on the scalability on resources or on energy efficiency. And we would like to have this connectivity anytime, anywhere. And this is even more relevant when we talk to access. We would like to have the fiber access, the wireless access, and the converged access between the fiber and the wireless. And somehow this is to be kind of manageable. Let it be even the manageability of a large amount of fibers, or even the manageability of the network itself. So if we look at these constraints, it's a good opportunity for the academic research to trying to come up with solutions. And this is what we do in my group. So we have a team that combines the expertise in communications, multiplexing, modulation formats, and the photonics, understanding fibers, lasers, diodes, and systems. And then signals is very important. Let it be in the channel, let it be the optical fiber or the wireless or the combined channel is very important. And then the synergy of those expertises is what we put together to come up with solutions to the challenges that I just mentioned. So the problems that we are tackling now, I have grouped in 4 corners, and one of those has to do with terabit short-range data links, and then we look at different type of combination of technologies, like a array of VCSELs, vortex or orbital angular momentum modes, multiCAP fiber, and we're actually not saying that this should be the way to go, but that these are new technologies that we are looking at because they have several promising features, and we want to find out where does it make sense, when does it make sense, and what it will take to actually make sense out of these solutions. And this is basically where I'm going to focus most of my talk today. We already saw some of the work of my group yesterday. We deal with the signal processing, and one of those is the coding and modulation formats, advanced modulation format, and also methods to predict, synthesize effects in the optical channel, and also applied machine learning algorithms to management, but also to monitoring and even for compensation of impairments. So that's one part of the activities. The second activity has to do with the fiber wireless, and then here we concentrate on using a concept from microwave photonics, concept from signal processing, and then trying to come up with solutions that can achieve tens of gigabits per second in the fiber simultaneously as in the air, and also moving forward into higher carrier frequencies like the sub-terahertz. And here the idea is to have a kind of connectivity anytime, anywhere, and some of the applications were highlighted yesterday here, like for instance the disaster recoveries and very high speed access. So another area of activities in my group is if we accept the idea that we are going to have photonics that is going to be controlled by software, like for instance one of the talks just before mine is on the flex grid, also the first talk today on flexible optical networking. We accept the idea, and we also accept the idea that the control is going to be software-defined control. That we are looking into architectures. We can actually try to put the functionalities as close as together, not only at the abstraction level, but also the physical level, on how can we combine software-defined control and software-defined photonics to make better use of the resources while we converge the method and the access. And this has a lot to do with the new generation of wireless systems that already integrate in itself the backhauling and fronthauling of wireless signals over optical links. So saying that is to give you an impression of the applications and also the expertise that we need to put together to come up with solutions. So one of those challenges that we are tackling is, but before that, the people behind, because the work I'm going to present is the merit of my students and my staff. So we have staff of, including myself, 6 persons. And then we have researchers, PhD students. Some of them are also chaired with other professors in the department. And then we have current 10 theses. They are master and bachelor students. And we integrate all these activities into what is going on in the group. So we can say that we have, in average, 20 persons working on different aspects of the activities in the group. So saying that, so this is the most valuable that I can say is the minds and the hands and the passion of my students that do most of the work. And then one of the topics. So one of the challenges is actually looking at the short range. And I take this example, which is the active optical cables. And usually today, the latest development and the promises is to have 120 gigabits per second with 10 to 12 arrays of VCSELs, and also the photodiodes. So if we would like to keep the increase of capacity, so either we need to increase the number of lanes, let it be electrical or fibers. So here what we're trying to do is to come up with solutions to reduce the amount of lanes and yet produce links that operate at 100 gigabits per second or above. So that is the challenge. What can we do to collapse these lanes into one? So one of the approaches, and the first one is very popular now, is what can advanced modulation format do? So our answer to that question is to look into the multiband, so that's the multi stands for, and then the carrierless amplitude phase modulation, so that's what is inside each of these bands. So it looks like DMT, but it's not DMT in the sense that we are using waveforms, orthogonal waveforms, so we are not using carrier, that's carrierless. And it has several advantages, that you can actually load different constellations and different bands. You can actually let the bands grow as you need it. And also it's flexible in bit rate because you can adapt the baud rate per band. And it's resilient to dispersion and actually has increased sensitivity. So this particular spectrum is taken from our poster line paper of last year OFC, when we can see that we use roughly 25 gigahertz of electrical bandwidth. So there has been an important result for the group because it gives an alternative and also gives a kind of platform that we believe is very flexible in terms of adapting to different applications. And that's why we decided to take this concept and move it into the even shorter range. So the previous one was on the O band. So this one is taking the same concept of multiCAP and then applying it to a multimode fiber link of 100 meters. So we use a VCSEL A50, and in this case we're still using the digital processing. What we can see is that in this particular case, with the devices that we have at home, we're able to put the same close to the 100 gigabits per second with using the devices off the shelf. This is a standard characteristic that you get from a commercial multimode VCSEL at 850 nanometers. Then this is a spectrum, as you can see, and then we see here some measurements on the end-to-end frequency response of the whole link. And what we try to look here is that it has a roll-off, but also you see that at 3 dB we are not using more than around 12 gigahertz. So with better devices, they could have a smooth roll-off. We are pretty confident that this is one way when you can already, with today's electronics, chips, VCSELs, achieve 100 gigabits over 100 meters, even more, of multimode fibers. So this is not published yet, so you will hear more details from my students in a few weeks here in OFC 2014. Okay, so what about the same concept for 400 gigabits per second? So that's what we did next. So we took the same concept, and we have in this case 4 EMLs. So we are talking now a little bit longer distances because it's targeted for the client side. We go back to the original O band. That's what you see here, 4 channels, and then we apply, in this case, 108 gigabits per second multiCAP. And we have 2 scenarios. Okay, let's see if we can reach 20 kilometers with no optical amplification, and then what happens if we actually use some kind of preamplification. So in this case, we preamplify up channels, and then we demultiplex. Different structure can be playing around here. So again, this is going to be presented in OFC, but the message here is that we have, in our search for solutions, we're trying to come up with a concept that can be applied to different scenarios, yet keeping the same complexity and looking into what is needed to be done to make it acceptable to the community. So 20 kilometers looks very promising because if we look at the bit error rate and the curves for all of the lines, so we have a pretty nice power budget. And here you see that we are not going over the 25 gigahertz electrical bandwidth. So that means that we could actually take 25 gigahertz optics and still run this system. We could actually make it with 10, 12 gigahertz, but then it's much harder to do it. So with this, I would like to move back to the short range, and is another attempt. As I said, we're trying to come up with solutions and interacting also with the end users. So why not to look at the WDM? So it's very well established in the long-haul community, less established in the multimode, but it's no showstopper in itself that we cannot use it. So this is an experiment that is going on right now in the lab, so I got just some recent pictures to show you. So we are looking in come up with systems that are simple, robust, and can use multimode fiber, and yet in this case we are reducing the amount of lanes in the fiber count. So we have 850 VCSELs again, 980. These wavelengths are the chips that I have available, either on chip mount or commercial devices, but it could be other wavelengths also. So just to give you an idea of the type of the principle, but I'm not saying that this should be the ideas. These are very interesting, 1050 or 1060, so interesting, but it also could be closer to the 850. So the basic idea is come up with 400 gigabits per second links that could be potentially be robust and compatible with the VCSEL technology. So this is how it looks like the experiment, the first part of the experiment with 2 channels. So this is the easiest one because this is a commercial packaged VCSEL, 850 nanometers, so it's somewhere here. And then the other one is a chip on mount, so it's a probe, and then a lot of cables and things. And here are the MUX and DeMUX, thin field based. So when we tested the VCSEL one by one, this is what you see. Nothing is particular, nothing special in this case. What you should expect: 25, OM3, OM4. OM3 here, OM4 here, and then we go a little bit more higher in bit rate, this NRZ. Then we do the same for 850, and already some nice things we start to notice. These are very new results that actually these fibers are quite optimized for 850, so you do that in this case they behave much better than the 980. But if the distances are short, there might not be an issue. So this is when they are independently and we are put all together. So in this case, these are already an end-to-end MUXIT and the MUXIT WDM link operating in both wavelengths. In this case, it's 50 meters OM fibers. So what is special here? In principle, is taking a concept from long haul, but trying to come up with solutions that will make it appealing for the specific application of low cost and robust WDM short links. Well, then we kept thinking, is there anything else that we can do? Because some of the predictions tell that we should look already 1.6 tera short data links. Okay, so then we came to the next kind of trick is to use the orbital angular momentum of light. So we have several nice talks introducing what it is, and actually instead of having phase front that are constant, that we have twist in the phase front, and the speed of twisting is what actually is giving us a different basis to multiplex. So this is how look at intensity and how look the twist in the phase. So the basic idea is that those can be used as a new base for multiplexing data. And this is what we intend to do in the next months, is to use the OIM of light for short-range communications. And as Mingli from Corning said, that might be very interesting because we don't need amplifiers, and there are certain nice features that we can employ for short range. So we started this work not so long time ago. So we are proposing a solution. This is just generic, so we think of some kind of multiplexing, and then multiplexing and fiber for short-range links, and then some way to generate vortex with the data. But our dream is to come up with a solution. We are looking for partners and cooperations that should be a solution based on VCSEL technology, because it will be very compatible with what is already being done in the short range. So where we are now, so we have taken one of the 850 nanometers VCSELs, and this is how it looks like, the spatial single mode. And then when we use that mode to generate vortex, these are the first experimental results for the vortex. And this is work carried out by Mario Suga, who is here in the audience, who can answer. So there's some impurities here. But that has to do because the VCSEL that we use in this first attempt is a multimode VCSEL, 850. Actually, the same one that's been used for the other experiment in the WDM. So it has several modes, and then we do some spatial filtering. Then we come up with close to single mode by the state. But this is not showstopper because we know that the development of single mode 850 nanometers is well advanced. So it's just that we need to replace our VCSEL for one of those single mode, which is going to happen soon. So at the moment, what we have is 22 gigabits NRZ. So this is just the electrical eye diagram to start with. You have an idea. So then we have put it into the OIM end-to-end transmission link. So it's a fresh space. So at the moment we are playing around with the sensitivity. So we're increasing the power that's coming to the photodiode after the OIM demuxing, and then we see they were recovering pretty nice. So this is also very recent results obtained by Mario before he took the flight to come here to this workshop. And in conclusion, so this is how it looks like at the moment. So the generation part, transmission part, detection part, and we can say that at this moment with this simple setup, we are able already to boost the capacity to 44 gigabits per second. This is very interesting because we would like to continue working in this area to come up with a solution that could get up to at least the idea is, does it work, what does it take, and what is needed to come up to a terabit short range link. With this, I would like to conclude. What motivates my team to look in this specific area is that there is a clear need for capacity upgrade of short range communication links. And there are different approaches we are looking at, and regardless of which approach we take, the solutions need to be energy efficient and they are very cost constrained. So I would like to invite you to follow us. We have a website which gives you easy entrance to different social media, where we have videos and logs we have publications and videos of the experiment being done in the group for more details. So thank you very much. Okay, thank you very much. So this question has to do over the fiber transmission. So right now in our lab, this experiment is done in the free space. So next step is actually to guide those modes in the fibers. Yeah, and in principle, the fibers they have been designed and tested for the C band, not the 850. They have shown little coupling among the fibers tested so far, up to 6. So I expect that if we are doing the computations right and the expectation right, then we should expect also the same behavior for the short range. Yeah, but that's things that needs to be done yet. Yes.
Thank you very much for a really exciting talk. In your opinion, WDM, you showed that 850/980.
Yes.
Is a combination, but obviously, I guess you could put a lot of more channels in there. So WDM multimode fiber, is it more or less promising comparing to the others?
It's a very good question. And I would say that for certain applications, when you have the links very short and you need very low cost, and then you have the freedom to choose the piece of fiber between the two ends, then maybe this is a good way to go. Very practical, short-term kind of way to go, provided we have low-cost MOOCs, DMOOCs. Yes. If it comes to short-range links that becomes part of the infrastructure, then they may be harder to convince that you have this type of infrastructure change. So it needs to work over the same multimode fiber, standard multimode fiber, and so forth. And then the question is not so clear. For instance, Google is pushing for an infrastructure based on single mode fibers. Yeah. So for cabling, I think the approaches I shown here, they have a lot of potential. Yes. Yeah. But as I said, I am now collecting inputs from also players in the industry on this respect. But definitely, it's very exciting to see that something that we assume it not so relevant has become a very relevant topic when you want to increase the capacity of short-range data links. Yes. Yes.
So for the WDM transmission, 980, the bandwidth is much lower than 850. Did you get similar performance? Or?
Yes. So the interesting thing is that we have seen a 25 gigabaud when we take an OM4 fiber. The 850 performs better with the devices and the setup we have than the 980. But if we take other fibers that have been designed to compensate for the chromatic dispersion, like the MaxCAP, then we see that the 980 performs better than the 850. So there is an interplay there with the fiber characteristics. Yeah, at high baud rates. Yeah. Yeah. But if we take short range, like for instance, one of the latest results, 50 meters, that we don't see that much. But the fiber characteristics, multimode fibers, like we have it today, yes, they influence a lot the performance. You move from 850 to 980. Yeah.
Your 980 is single mode VCSEL or multimode?
It's a multimode. Yes, yes. And I will perhaps need to get back if I need to check the spectra. Yes, yes, a multimode.